So now we talk about optimization. And in my opinion, at least for you guys in business calculus, optimization is the crown jewel of differential calculus applications. That's what we've been doing, differential calculus, taking derivatives and figuring out how to use them. And this allows us to answer all sorts of fun questions by applying our calculus. So let's see. Here we have a rectangular garden, all right. So what I'm going to do is I'm going to draw a picture of a rectangle. Okay, we have a rectangular garden constructed using the side of a building as one side and fencing on the other three sides. Okay, there are 116 feet available. Determine the dimensions that would create the garden of maximum area. What is the maximum area? Enter only the maximum area. So here we have the side of the building, and we're wanting to make an enclosed space right here with our fencing. It says that we have this much fencing available, and so to maximize the area, we're going to use all that fencing. Okay, and you can make all sorts of different type fences. I could make one that was 1 foot on each side, and then 114 feet right here. Now that would not be a maximum area. That would only be 114 square feet. I think we can do better than that. So that's what the optimization process will help us do. Now we don't know what are we trying to maximize here? We're trying to maximize the area. I need an area function. I need an area function so that I can take the derivative of that area function. I'm going to take the derivative of that area function, and I'm going to find out what its extreme values are, right? In particular, the absolute maximum. Okay, well that would mean I would need a closed and bounded interval for this area function, and that's going to end up being the domain, the reasonable domain associated with this constraint. Okay, so let's see. We could now I know that area is length times width. Let's start there. And so let's call this the length and this is the width. Then that means that this is also the width. All right. But now I'm going to use my constraint, because that 116 feet of fencing must go here and here and here only. And that means that if I let this be my variable, let the width be our variable, then I can swap out the length for, I can rewrite that length in terms of the width. Because this is the constraint, then it must be the case that this length uses 116 feet of fencing minus 2 times W, because it's minus this W and minus this W. Well, then you would have that this length plus this width plus this width would end up being 116 minus 116 minus 2w, because that's what L is, and then plus w, that's plus 2w, well then this clearly adds up to 116. So I am using all 116 feet of fencing in this way. And I can come back over to my area function and say that this length is now 116 minus 2w. And now I have a function of w. It's only got w. Now if I go ahead and distribute that w in just to make the derivative easy, then I would have 116w minus 2w squared. And this is my area function. This is the thing we want to maximize. So when I take the derivative of that area function, I would be getting 116 minus 4w. Okay, well, 116 is divisible by 4. You would get, if I factor out the 4, then I would get 29 minus w. In turn, I know that my critical value is when w is 29. Okay. We need to know that that is where the absolute maximum will occur. Well, what was the domain of this area function? Well, first of all, observe that this is a quadratic that opens downward. So that means it's shaped like this. So it doesn't matter what that closed and bounded interval was, the maximum will occur at the critical value. But just to get comfortable with writing down the domain, what is the smallest possible value for w? Well, there isn't one, actually. Let me say it like this. If w were to collapse all the way down to 0, then we would no longer have an area. So my interval must be that w is at least greater than 0, but there's only 116 feet of fencing available, so w must also be less than a half of 116. Which is 58. So my domain here would be 0 to 58. It's actually not closed, so I wouldn't even be able to use my extreme value theorem. I just have that this is the maximum value, or this is where the maximum value occurs. Okay, so then they want me to enter in the maximum area. Well, that's going to be when the width is 29, so I'm going to have 116 minus 2 times 29 times 29. That's me using this version, just so I don't have to find 29 squared. So 116 minus 2 times 29, well, that's 116 minus 58, which is just 58. So this says 58 times 29. And I get that that is 1,682. So this is the maximum such area. Up next, we have a bike rental company. Now let me tell you guys something. I've seen this question before. Where have I seen this question before? I've seen it on the test. It might as well be this exact problem. So pay attention to this problem, because I'm pretty sure you're going to see it again. A bike rental company charges its customers this amount of dollars per day, and they give us the closed and bounded interval for where this function lives. Okay, between 5 and 30, including 5 and 30. And that's how much they charge their customers. The number of bikes that can be rented, the number of bikes as a function of the price they charge. So it's kind of like the demand function is 300 minus 10p. How much should the company charge each customer per day to maximize revenue? Oh, well, we have a couple of ways of doing this problem, don't we? Because on the one hand, we recognize that this n of p function is just a d of p. And so you could, we know that the elasticity, wherever the elasticity is 1, that this will be where the revenue is maximized. But I think that we can now be able to investigate why this was equivalent to just the regular old optimization technique of writing down the revenue function and finding out where it has a maximum. And I tried to do that for us when we first looked at elasticity of demand. I gave you the simplest possible derivation of it that I could think of, because this is the number of bikes as a function of price. So it's a demand function. And if I were to be able to write down the revenue function, revenue as a function of price is just the number of items that you sell times the price. The number of items you sell times the price. This tells you how much revenue you brought in. And that number of items is n of p, and then times the price. So the revenue function we are looking at is going to be 300p minus 10p squared. And we would take its derivative, and we would take its derivative and set it equal to 0, find the critical value. We can see that it's going to be a maximum because this is a quadratic that opens downward. So then what would be that derivative function? Let me do it here off to the side. So r prime is going to be 300 minus 20p. Okay, so if I factor out that 20, then I would have 15 minus p. And so p would equal to 15. And that this is where, if I charge this much, then revenue would be maximized. But I could do the same thing here. I could do the same thing here. Because this right here is our revenue function. Let's just keep that off to the side. But looking at this elasticity of demand function and insisting that it equal 1, well, let's multiply on both sides by this d of p. Well, then if I did that, then I would just have that, I would have my d of p times 1 over here, and then the other side would just say that. Okay, well, that would be 300 minus 10p equal to a minus p times the derivative of this. And the derivative of that is just minus 10. So it says 300 minus 10p equals to 10p. And then let's subtract that 10p over to the other side, and then you'd have 300 minus 20p equal to 0. Well, look at that. 300 minus 20p equal to 0, and that's exactly what we did here. 300 minus 20p equal to 0. So in either case, you get that the price is $15 is what they should charge in order to maximize their revenue. An open top box, so that means it has 5 sides, is going to be made from a piece of plastic that's this big, 70 by 96, and they're going to do this by cutting a square out of the 4 corners of that plastic sheet. So we have a piece of plastic. It measures 70 by 96, and they're going to cut some kind of square out of each of the corners, and then they'll fold it up into a 5-sided box by folding along this red dashed line. And okay, great. So now they're asking me what size of square should be cut in order to maximize the volume. So volume is the thing we want to maximize. So an equation for volume is what I need to write down. And it's going to be as a function of some variable. I don't know which one. But for now, I know that volume of, when I fold this thing up, it'll be a rectangular prism. It'll be the volume is length times width times height. Length times width times height. Okay, great. Let's call the size of the squares. Let's just say each of the side lengths of the squares is x. Right? They're squares after all, so the side lengths are the same, and we don't know what they're going to be yet, so we'll call them x. Then you can see that once this box was folded up, it would have a height of x, wouldn't it? The box would have a height of x, so I'll replace the h with x, and now I'm thinking that this volume function is probably going to be a function of x. So let me replace the height with an x, and then now let's talk about, I guess, the width. We're going to designate the length as the longer edge and the width as the shorter edge. So this would be our width, and this would be our length. And how can I say what the width and the length should measure? Well, if I come back up here, that means that this segment is the width, and this segment is the length. So what I can see is that this width should be, the width is going to be 70 minus the two x's. That width will be this entire 70, take away the x on each end, and you'll just be left with the width. So there's my width, and in the same fashion, my length would be 96 minus 2x. And now I have a function of x. Now I have a function of x, and it's going to be a cubic function. It'll be shaped like this. So it'll have a local maximum and a local minimum. Okay. Now you could multiply all this out so that you could take the derivative term by term. I'm thinking of if there's a way I could do that without having to do that. I mean, I could just distribute this x into here and then use just a product rule, and that seems like it might be easier, but in either case I'm going to have to end up multiplying some stuff along the way, so I guess I'll just multiply this thing out. So v of x is going to be, well, I should FOIL these two things together, and then when I'm done I'll just multiply everything by x. And I don't want to figure out what 96 times 70 is yet, so I'll just write it like that. 96 times 70, and then minus 2x times 70, and then minus 2x times 96, and then plus, I've written too big here, let me write smaller. Okay, and then the minus 2x times the minus 2x gives me plus 4x squared. And then I have all of this times x. Okay, and what I see is that right here, both of those have a minus 2x. So I'll just factor that out. 96 times 70 minus 2x times 70 plus 96. And I guess I should go ahead and multiply everything by x. This is 96 times 70 times x minus 2x squared times 70 plus 96 plus 4x cubed. Okay, great. There's my v of x. Now I need v prime. In order to find my local maximum. Well, v prime, I'll just differentiate term by term, and I'm going to get 96 times 70, because that's the constant, minus 4x times 70 plus 96, whatever that is, and then plus 12x squared. Okay, great. This is a quadratic function. So it's going to have two zeros. And let me factor out the greatest common factor so I can make it easier on myself to factor this thing. I believe that 96 is divisible by 12. Yes, it's 8 times 12. I don't want to factor out 12, I want to factor out a 4. So 96 is 4 times 24. So I have this then. All right, and I guess now I need to, well, can I factor out a 3? I guess is the question now. 70 plus 96 is 166, so now can't factor out a 3. So let's write it like this. We have 4 times 3x squared minus 166x plus 24 times 70 is 1680. So then this is the polynomial to factor now. Okay, then I will use my strategy that A times B should be equal to 3 times 1680, which is 5040. And then A plus B should be equal to a minus 166. And if I can find the numbers A and B that satisfy that system, then I will rewrite this polynomial like 3x squared plus ax plus bx plus 1680, and then it will factor by grouping. So let's see if we can solve this system. I'm going to start with the sum here. I need some candidates for that sum that add up to minus 166. So how about minus 100 minus 66? Well, that's 6600. That's 6600, which is bigger than 5040. Right? So I need to, this adds up to minus 166, but their product is 6600. So let me try something else. How about, now this ends in a 0. So I know that it has to be 10 times some number. It has to have a factor of 10, put it like that. So maybe I should try minus 70 minus 96. No. Because that's even bigger. So what about a minus 110 minus 56? No. What about minus 120 minus 46? No. What about minus 130 minus 36? So that adds up to minus 166, but the product here is 4680. And on the previous one, the minus 120 minus 46, the product was 5520. So that tells me if there's an answer, it must be somewhere in between these two. And since I know that 5040 has to have a factor of 10 because it ends in a 0, then it also must be the case that the two numbers I'm multiplying have a factor of 10. One of them must end in a 0. Well, there's no more room between 120 and 130 for a number to end in 0, so my only choice is to make this one be a minus 40. So minus 40 over here, and that would mean I have a minus 126. Let's see. And sure enough, that does it. Because minus 126 minus 40 does add up to minus 166, but their product is 5040. Okay, great. So then what I will do is come back up to my polynomial I'm trying to factor and say that this is 3x squared minus 126x minus 40x plus 1680. And now it will factor by grouping, which is way easier than trying to factor that thing by the high school method of guess and check. That method would be so hard in this case because there are so many different factors of 3 and 1680 that it's just way too much to try and figure out. And this system is more methodical. Okay, so now factor by grouping. I will look at these two factors and see what they have in common. 126 does have a factor of 3. It's 3 times 42. So from these first two factors, I'll factor out a 3x. And then what's left is x minus 42. And then I'm guaranteed to also have an x minus 42 over here. In fact, that can guide me as to what must factor out of these. It looks to me like a minus 40 is going to have to factor out. Well, is it true that minus 40 times minus 42 is 1680? Sure enough, it is. So there we go. I've now got my, I've started the factor by grouping. So then now I have two terms. I have this term and I have this term, and each of them have that x minus 42 in common. So let's factor out the x minus 42. So the final factorization of this thing looks like this. There we are. So then the critical values of the volume equation that we had would be 42. My critical values are 42 and a minus 40 over 3. Excuse me, not minus 40 over 3, positive 40 over 3. Because if I put 40 over 3 right here, the 3's would cancel, and then it would say 40 minus 40. Now I already told you that the shape of that cubic function was like this. All right, so that's telling us that where those local minimums and local maximums occur. It must look like this because 40 over 3 is less than 42. All right, so then that means that our original piece of plastic that we were going to carve up so the squares we're going to cut out have side lengths that are 40 by 3, And this long edge, or this edge was 70, and this edge was 96. And there we are. Now the question wants to know, enter the area of the square and do not include any units in your answer. So 40 over 3 squared is that number, right? 40 over 3 times 40 over 3 is 1600 over 9.